Hello everyone, welcome to AWS reInvent. My name is Imtiaz Syed. I'm the worldwide tech leader for Big Data Analytics, here today with Jacob Lockhart from the British Telecom Group. Our goal today is to talk about real-time streaming on AWS, with a particular focus on Amazon Kinesis data analytics, and then have Jacob dive into the British Telecom experience. The AWS streaming options include several fully managed services that support the collection, processing, and analysis of streaming data in real time. The Amazon Kinesis data streams captures data in real time. Think gaming data, sensors, mobile feeds, and so on. Next, we have the Amazon Kinesis Data Firehouse for buffering real-time use cases before sending data downstream. It natively supports several AWS data stores and HTTP endpoints, including many popular SaaS providers. This is followed by the Amazon Kinesis Data Analytics, a service that processes real-time data streams with Apache Flink and SQL. We'll come back to this one in a little bit. The Amazon Managed Streaming Service for Kafka, or MSK, is a fully managed service to run Apache Kafka. We have several MSK sessions lined up that talk about it in detail. And then the Amazon Kinesis Video Stream Service that supports secure video streaming from connected devices to AWS. Today, we'll be focusing on the Amazon Kinesis Data Analytics with Apache Flink. Let's take a quick look at Apache Flink. It's an open source, event-driven, unified stream and batch processing framework that provides rich and layered APIs and delivers guaranteed state while running applications at any scale, and is supported by a very active community, including AWS. And Amazon Kinesis Data Analytics. It's a fully managed Apache Flink service that is a serverless experience designed for very low latencies. And it takes away the complexity of managing Apache Flink applications. It scales automatically to match the volume and throughput of your incoming data, and you only pay for the resources your app uses. There is no minimum fee or setup cost. Here's a behind-the-scenes look at the service. It deploys Apache Flink using Amazon EKS, a fully managed Kubernetes service. The Apache Flink cluster is run in a highly available mode with Apache Zookeeper across multiple AZs. The service backs up application state to Amazon S3 using checkpoints and save points. By adding an Amazon CloudWatch logging option, you can monitor for custom events and configuration issues. And now, you can also leverage the Apache Flink dashboard to monitor health elements such as watermarks, back pressure. Moving on, we touch upon a few operational elements of the service, some of which Jacob shall be expanding upon later in the session. Save points are snapshots, and checkpoints provide a recovery mechanism in case of unexpected failures. The state of the data is stored in RocksDB, a persistent key value store, and performs the incremental checkpoints to S3. For monitoring, you have a logging option to write metrics and events to CloudWatch and CloudWatch logs. To scale, you can configure parallel task execution via properties like Parallelism and Parallelism per KPU. You can also monitor the CPU usage of your application and elastically scale your Parallelism. And for costing, you are charged an hourly rate on the average number of Kinesis processing units, KPUs. One KPU is 1 vCPU and 4 GB memory. There's also additional storage cost. At this point, I would like to thank you for your time and pass over to Jacob from British Telecom to talk through his experience and share best practices towards managing state, troubleshooting applications, and monitoring. Thank you.
Hi there, thanks Taz for that introduction. I'm Jacob Lockhart. I'm a software engineer at BT, based in Belfast in Northern Ireland. So here's the agenda for the presentation. So for the first few minutes I'm going to talk about the background of the project and then give a rundown of the requirements that we received from the business. Then I'll dive into the KDA side of things with Apache Flink, so how we use those components to realize those use cases over a few subsections here. So these are keyed stream joins and managing state, how we performed real-time enrichment of data in a data stream using a static reference table. Parallelism and scaling, so how we configured parallelism in KDA and auto-scaling according to throughput. Custom metrics integration with CloudWatch, so I'll give an overview of the out-of-the-box metrics support and also how you can use KDA to post custom metrics from within your application code. Then just a short section on our use of Scala and its trimonad to help maintain uptime. Then finally I'll go over the technical and business outcomes of using KWA on AWS. So a bit of an overview of the use case. About a year ago, we got a request in from the business to build a service monitoring application to support the rollout of digital voice. Digital voice is BT's new consumer voice product, which provides HD voice calling capability over our broadband network in the UK. So over to the right here, you can see this diagram of the flow of a simple digital voice call, all going all over broadband using handsets similar to landline ones you'll recognise. Digital voice customers, they can make and receive calls to and from non-VoIP destinations as well as mobile destinations as well. So there's a few requirements that came in from the business. They needed a 24-hour, 7-day-a-week view of the network with call data landing ready for viewing in some sort of dashboarding tool in real time. Without this, the rollout was at risk. They also needed actionable insights based on service experience. So this means that the data should be useful enough to be used to spot, diagnose and solve any issues in the network. The system has to be scalable. The service is going to roll out over the next 4 or 5 years. So this posed a few technical challenges to us. Up until that point, pretty much all of our data processing jobs ran on an internal Hadoop cluster. This Hadoop cluster really had no room at all for this type of real-time job, because the cluster is shared between a number of different teams around BT. The only way we could feasibly scale the cluster was by buying new hardware and manually installing it, which of course comes with quite a high price tag. It's also a non-managed service, so any upgrades, they're managed by an internal team. So upgrading and testing involves that team. Also around real-time enrichment of the data, and really any sort of purely real-time data processing was just out of the question because of these capacity issues. So we carried out some preliminary work because we came to the conclusion quite early on that our on-prem hardware just wasn't going to fit the bill. So then we looked to the cloud. So first stop for us was AWS. We wanted to prove out an MVP solution to see if it would work technically for us and also financially for the business. We submitted our idea to an internal hackathon, which AWS were associated with, who were a great help during those few days. We managed to build an MVP in about 2 days. So what that MVP showed us was that with AWS, with Kinesis Data Analytics, it filled those requirements for a real-time event-driven analytics service at a reasonable financial cost. So it's definitely something that we would confidently propose to the business. So a bit on our on-premises solution. Those requirements that came in were quite urgent. So before building a fully productionized system on AWS, we built an intermediary service on our on-prem hardware. So from this diagram we can see we used Kafka for our data ingest and Apache Spark for the data processing and then Splunk for our visualizations. The home hub device that makes the data post into the service in this project, it posted at a 15-minute leaf schedule. So already there's going to be latency introduced by the limitations of the on-prem system. So it's processed by our service, which is all physical hardware, which of course limits scalability. The processed data then is exposed to a service monitoring team via Splunk. So this already has a few disadvantages. I mentioned before around scaling and provisioning new hardware, but also the data itself. Since it's posting every 15 minutes, the data it's always going to be out of date. So a bit on our proposal or on the cloud. So the intermediary solution, it gave us time to architect a fully productionized solution that would run on AWS. I'll briefly go through the architecture here before diving into the Kinesis analytics side of things. So first off, each home hub in the field, it makes a data post as soon as the call ends. This looks like a JSON document. It contains details about the call that's useful to the service monitoring team. So this post arrives at the front end. It goes through Route 53 for DNS, then into WAF, which applies some web ACLs that we've configured. ELB then load balances the post into a scalable ingest server, which is managed by Fargate, something that we have written, which does authentication with credentials stored in Secrets Manager, and then along with some other minor transformations. The server, it then forwards the data onto a Kinesis stream. So I mentioned earlier, KDA enriches the main data stream. That was a requirement that came in. So it enriches with some static data stored in our on-prem cluster. So it's streamed up onto two separate data streams, which are then loaded into the KDA application. Then the application outputs all the fully transformed data into CloudWatch, which forms the basis of our visualizations and the alarms for the service monitoring teams. So a bit of a side-by-side between these two solutions, our on-premises and our proposed cloud. Our cloud proposal, it brought us into the world of event-driven real-time streaming over the batch processes that we have on-prem. Also quite a large increase in the proposed volumes. On-prem at peak was around 30,000 customers, but in the cloud this goes up to about, at peak in a few years, will go up to about 6.5 million. Our latencies in the cloud drop as well to under 3 seconds, as well as the ability to enrich the incoming data in real time. Ops-wise, on-prem, it's pretty unstable. Very little room for building an ops monitoring wrap around it, and dealing with physical hardware and the stresses that that brings. But on the cloud, the end user has dedicated serverless resources on AWS with a full monitoring wraparound built in CloudWatch. And just for clarity, the deployment of the service into the cloud, it isn't a migration at all. It's a completely new system. The intermediary solution, it was just put in place to provide some minimal level of service to the monitoring team until a full real-time service was made available. So I'm going to go into the main technical portion of this presentation about KDA with Apache Flink. So I'm going to focus in on how we use KDA and Apache Flink to fulfill the requirements I just talked about. So just a reminder, just around real-time, these are all around real-time enrichment of the streaming data with geographical data, parallelism and scaling metrics, and then a bit on Scala at the end. So a common use case when developing streaming applications is the need to enrich your main ingest stream with some metadata stored in a static table. So something that the business asked for was the ability to localize a call session right down to the network hardware involved in transporting that call, so that as much geographical information can be used to diagnose and fix any issues that arise by the correct teams. So this enrichment data, it's stored in a table on our on-prem Hadoop cluster. We stream this data into a Kinesis data stream, which is then read by the Kinesis Analytics application as soon as it comes in. There is an additional metadata stream upload, which I won't go into, but basically we use that data to categorize different call types. So a bit more on the geographical enrichment. KDA gives you the ability to join two data streams together, all in real time. So first off, we load our main data stream into the KDA application. This stream contains a day's worth of data from the geographical data set. So you can see some of the anonymized columns here. There's hub identifiers, the region that hub is in, some of the network interface hardware, and things like that. So down here, there's our main ingest stream. So that's data coming in from the hub posts. So it also has a hub serial identifier, and it's just other details about the call that just ended. So to join these streams, we do what's called a key-based join, where two streams are joined on one or more keys. So it's helpful to think of this as a join between two database tables, which they can be joined together on one or more keys. So we key each of these streams by serial number, so that they are joined on similar serial numbers. We write something called a flat map function, which processes both streams, and which is used by KDA to actually carry out the join. So basically, when a record on the left-hand side comes in with a matching serial number to a record on the right-hand side, the two records are joined together. So then the join stream, it goes out to our egress stream processing. So a bit on managing state. So during that stream join, state needs to be stored so that it can be updated and read. KDA provides an interface to manage state during a join so that the data is easy to access and it's always up to date. So we found that managing state with KDA was a great contributor to the system's uptime. In the past, writing stream jobs in our on-premises kit using Apache Spark, it followed this flow here. We would basically have a daily upload of any metadata to be used for enrichment going into our Spark cluster. We would then schedule a daily restart of the Spark jobs to refresh the metadata so that the main streaming data is enriched with up-to-date data, which is unfortunate for us because it basically guarantees a few minutes of downtime every day, which adds up over a long execution period. However, on the cloud, we can simply upload our metadata into Kinesis data stream, which is then read by the KDA application as soon as it arrives. The KDA app immediately stores the state internally, and then it's used in any subsequent data stream joins. And all of this is done without having to restart. So going a bit behind the scenes with state management now, in our stream join code, we used Apache Flink's value state to store data coming in from the enrichment geographical enrichment stream. So value state basically stores a value that can be updated and retrieved. Each value is scoped to the key of the input element. In this case, it will be the serial number of the current geographical enrichment record in the stream. So value state, it uses RocksDB in its backend to persist the data, which allows for very fast reads and writes when the data needs to be read or updated. Apache Flink, it provides a simple interface to RocksDB through the value state so that you only have to worry about the essentials. Apache Flink does the majority of the RocksDB configuration behind the scenes, so you don't have to. So something exposed to you is the ability to set a retention policy or a time to live on the data that the value state stores. So in our configuration below, we've set our TTL in seconds, which we bring in from a config file. We also have an update type of onCreate and write that specifies when the TTL is refreshed, and then a state visibility of never return expired. That means that any expired values that haven't been cleaned out yet by the state management service, they aren't returned if they're requested. KDA and Apache Flink provides quite a lot of low-level parameters like this to allow you to fine-tune your streaming application. So another important technical requirement for us was around scalability. So there are, due to the nature of the data, there's peaks and troughs throughout the day as the call records are generated by phone calls. Call volume peaks during the day and then tapers off during the night. So on top of this as well, the rollout of the digital voice service, it's still ongoing. So we'll be seeing a linear increase in call volumes over the next 4 years as well. So it's important to us that the service is automatically scalable and also has high availability as it runs for 24 hours a day, 7 days a week. So Kinesis provides scalability right out of the box with a Flink application configuration block under the Parallelism configuration when you're deploying your application. Kinesis processing units, or KPUs, these are standard measures of capacity provisioned by Kinesis. So a single KPU provides you with one virtual CPU and 4 gigabytes of memory, and also 50 gigabytes of running application storage. So we did quite a lot of experimentation and test under different loads to get to these values that we have selected. So these are going to be completely different for your use case. But something I would definitely recommend is testing different configurations and combinations of these values, especially under a non-functional test. So going into operational metrics then and support in CloudWatch. So like other AWS components, KDA has native support for CloudWatch metrics, which can be used to monitor the service itself. So a few examples that we have included in our operational dashboard that we have built are around data throughput, heap memory usage, active thread counts, and then counts of records passing through the stream. Some of the metrics that we have not included here, but we've used to track the stability of our service, their stream downtime, and the count of full stream restarts. So we found these very handy in testing our application, as you could see exactly when any issues occurred that weren't caught by your error handling logic. KDA also gives you control over logs that Apache Flink outputs when processing the data. So Apache Flink outputs its own metrics, which we'll see in the next slide, as well as any debug or task level logs straight into CloudWatch for your analysis. So as well as standard operational metrics outputted by the service, you can use Apache Flink to actually configure your own custom metrics generated from within your application code. So these can be used to track application-specific metrics that aren't supported by default. So KDA with Apache Flink provides a number of different metric types depending on your use case. I've included a link to some AWS documentation of these in the references at the end of this slide deck. But for one of our use cases, we implemented a counter in our geographical enrichment code. So all we need to do is instantiate the counter from the runtime's context, give it a name. In this case, we're counting the number of incoming records that don't have an associated key in the geographical data set to join with. And then down here in our join code, if there's no associated right-hand side value, so basically if the value retrieved from the value state is null, then we increment the counter. Then Kinesis Data Analytics, it handles the rest, and the metrics are posted automatically into CloudWatch. Having these operational metrics that come by default and also the custom application-specific metrics, it has really increased end-user confidence in the system. KDA makes it very easy to configure low-level metric collection. So very briefly on our use of Scala, our use of a design pattern that we found helpful to actually mitigate against any system downtime. So we used Scala's try-monad to wrap our data stream model classes. So try basically represents a computation that can output either a valid result or an exception if something goes wrong. So if somewhere along the line during the stream processing logic we encounter an exception, it's wrapped up in a failure and propagated right through until the very end of the program, where it's handled by an exception handler. It goes through the same logic as the data wrapped in the success, so actual valid value from the computation, and goes through that logic, only that it's ignored by the application code until the very end. So that ensures that any errors are handled appropriately and they don't actually bring the system down unexpectedly. So the outcome, has all this worked for us? I can say yes. The functional outcomes. So here's a table similar to the one at the beginning, which shows our initial requirements that we got from the business and also the value that AWS with KDA has provided. So with KDA, we've enabled a full event-driven streaming architecture. So as soon as the data is generated from the call, it's processed and outputted from KDA. We have seen reduced latencies of over 15 minutes on our on-prem hardware right down to 3 seconds, under 3 seconds. That's from the hub post out in the field over the internet into our system and out onto a data point in CloudWatch. So that means that the data is always going to be up to date for the end user. So we have enabled the enrichment of the main data stream as well with geographical data using key-based stream joins. So the data is useful for tracking any network faults that might arise. The state management is not something we need to really worry about because KDA with Apache Flink handles it all very well with RocksDB. So that adds to the overall system stability. Auto-scaling as well, it's enabled with the built-in support for Parallelism. It's extremely valuable for us as the rollout of the digital voice product gets ongoing for the next few years. So we have a very high guarantee around stability because of the state management, the ops monitoring, and with the metric logs that we've enabled. That means that our internal support teams, so the guys that monitor this actual program, they get the ability to monitor that, which increases our end user confidence as well. So all of this, it's fully managed by AWS. So the stress and infrastructure management, it's offloaded in favor of a serverless approach. So from the business side of things, as I mentioned before, data arise into the end user's dashboards very quickly. So decisions can be made on the most recent data points. If a network fault begins to arise, we know about it pretty much immediately, compared to at least 15 minutes delay on premises. So there's no upfront cost for shared resources. The business pays for what they use, nothing more than that. And this is opposed to sharing infrastructure on-prem with other teams in BT. So a great bit of feedback from the end user was that they were able to use this service to spot and diagnose a major network fault in about 30 minutes, which is something that apparently the other existing monitoring tools that they've been using didn't even flag up, which is a great advantage of having that up-to-date data. So the solution we've developed, it can be used as a baseline for new monitoring tools we will choose to build on AWS, which reduces development overhead and time and costs for the business. Just a note on the scale of the project. The solution itself is part of a countrywide product rollout with potentially millions of customers over the next few years. This enables really fine-grained support of this rollout, which is great. And finally, operational costs are very manageable for the business, which is always good. So here's some references around digital voice as a product, and also just to supplement the technical aspects of this presentation. But yeah, thank you for tuning in, and make sure you fill out the session survey. Thank you very much.